Hello everybody. Alright, let's keep going. So if you remember, the radioactive isotope that's doing the decaying is called the parent isotope. And that's going to decay to the daughter isotope. Now the daughter isotope by its very nature must be stable, so it doesn't want to decay any further. Now if you remember, earlier on we saw an image of a decay chain. And if you looked at the decay chain, it had loads of intermediate steps before you reach the stable daughter isotope. Well, those intermediate steps are not the daughter isotope because they are not stable. Now, the rate at which a parent isotope decays to the daughter isotope is actually constant, which is extremely helpful because if you think about it, it's going to be like a clock. So if we have some of the radioactive isotope in something like a mineral, well, we know that that parent isotope is going to be decaying at a set rate. So it's going to be 1 decay, 2 decay, 3 decay, 4 decay, 5 decay. It's just like a clock, isn't it? So we can use these decays to help us date minerals and thereby the rocks that those minerals came from. So we just need to know a few things. So the first thing we need to know is how much of the parent isotope did we start with? Now that one's relatively easy to work out. So if I take a mineral now which I want to analyze, okay, the first thing I need to make sure I know is that it didn't contain any of the daughter isotope. Okay, so let's talk about uranium-235 to lead-207. Okay, so this is what we're going to talk about. So as long as I know that my mineral contains uranium-235 initially, but did not contain any lead-207, I can use it for dating. The reason being is that I want any lead-207 I find in my mineral to have come exclusively from the radioactive decay of uranium-235. Okay? Now this means, okay, let's say my mineral formed, 1 billion years ago. Obviously, over that 1 billion years, the uranium is going to be decaying to lead-207, isn't it? Yes? So the uranium-235 is decaying to lead-207 at a constant rate, just like a clock. Okay. So I come along 1 billion years later, and I take the mineral out, and I analyze it. So what do I analyze it for? I analyze it for two things. I analyze it for the amount of lead-207. Because, remember, the lead-207 in my mineral can only have come from the decay of uranium-235. The other thing I analyze is how much uranium-235 is left in the mineral. Okay, so what do I do with that? Well, if you think about it, when a radioactive decay happens, all that happens is I take one atom of uranium and I turn it into one atom of lead. I haven't actually lost any atoms, have I? So in order to work out how much uranium I started with, all I have to do is add together the amount of uranium-235 I have now and the amount of lead-207 I have now. If I add those two numbers together, I get how much uranium-235 I started with. So I know how much uranium-235 I started with, I know how much uranium-235 I have now, and because the decay is constant, I can then calculate very, very easily how long it would take me to get to the amount of uranium-235 I have now from the amount I started with. And that's it. It's really that simple. At the most basic level, radiometric dating is a breeze. Now, it's not actually that easy because nothing in life is that easy. So obviously there are going to be problems, kind of from a chemical and isotope point of view, but there's also the problem of the amount of uranium and lead you're dealing with are minuscule in these minerals. It's tiny, tiny, tiny amounts. So that means you need to use very, very sophisticated techniques to be able to extract them from the mineral and then measure them accurately. So, this is not an easy process. It's time consuming and it's money consuming. So that's why we don't actually do, radiometric dating of minerals all the time, because it just costs too much. Now, because the rate at which a mineral decays is constant, it allows us to essentially define something which we call a half-life. And a half-life is defined as the amount of time required for 50% of a radioactive isotope, so that's the parent isotope, in a given sample to fully decay to a stable daughter isotope. So essentially it's how much time is required for 100 atoms of uranium-235 to decay to lead-207. Okay, now the half-life will vary for different radioactive isotopes. So if we look here, the half-life for hydrogen-207 is about a billionth of a second. In contrast, the half-life for tellurium-128 is, well, this number here, which apparently, according to Google, is 2 septillion years. Okay, so half-lives vary between different isotopes. All right, just bear that one in mind. So the other thing about radioactive decay is that it's not a uniform linear change. So it's not like drops of water going into a glass. So every time a drop of water falls into a glass, the level raises up by the same amount each time, doesn't it? Half-lives aren't like that, and you'll see that in a couple of slides when I show you some graphs. Okay, so we've already discussed this, but as long as we know how much of the parent isotope we started with, and how much we have left when we measure the mineral, all we have to do is calculate how long it would take for us to actually have achieved that change in the amount of the parent isotope. So this process of radiometric dating is very, very straightforward. And the half-life essentially is the measure that we use to say, right, what is the rate at which this radioactive decay happens? So here we go, radioactive decay. So this is relatively straightforward. So here we go, we're starting with 1,000 atoms of our parent isotope. So half-life 1 will be when 1,000 atoms of the parent isotope has decayed to 500 atoms of the daughter isotope. Now that means after one half-life we will have 500 atoms of the parent isotope left and 500 atoms of the daughter isotope left. Alright, everyone feeling good so far? So the problem is though, the process doesn't stop after just one half-life, it keeps going. So then we're going to go to half-life 2, and that's when half of this number, half of the 500, has decayed to 250. So by this point we have 250 parent isotopes and 750 daughter isotopes. Now to be clear, the amount of time it took to get from here to half-life 1 and from half-life 1 to get to half-life 2 is exactly the same. Okay, so the amount of time to get from here to here, let's say it's 1 billion years, is the same amount of time required to get from here to here. It'd be a billion years. The other thing you'll notice is that the amount of parent plus daughter isotopes equals the amount that we started with. So we're not losing anything, we're just turning one atom into another atom. Same here, 250 plus 750 equals 1000. So you can see this is not a linear change. Okay, so in this case we're starting with 100 parent isotopes. Half-life 1, we now have 50 of the parent isotope left. Half-life 2, 25 of the parent isotope left, so it's half of the previous number. By half-life 3, we have 13, it should really be 12.5. By half-life 4, we're down to 6. Okay, should really be 6.25. So you can see that each time we're going down, we're dividing the amount of parent isotope in half. Okay, but the amount of time to get from here to here, from here to here, from here to here, and from here to here is exactly the same. So getting between that point, that point, that point, and that point, that point, and that point is a constant. The number, the amount of time required does not change. Okay? So that's why half-lives are so helpful to us. The other thing that's very, very important is that as the amount of parent isotopes decreases, the amount of daughter isotopes, of course, increases. And it's a very simple calculation to work out what the number of daughter isotopes should be. As long as we know how many we started with, 100, and we know how many parent isotopes we have, let's say in this case 25, well, we know the number of daughter isotopes must be 75, because these two numbers added together must equal 100. All right, all relatively straightforward. Okay, so what about common radioactive decay? So what are the common radioactive minerals out there? Well, obviously we have uranium and thorium down here. Those will be the ones we're all familiar with. But there are also radioactive isotopes of carbon, potassium, rubidium, and strontium. Okay, even samarium down here. And we can use all of these to date different minerals. Okay, now the half-lives will be different for each of these radioactive isotopes, and the techniques we use and the minerals we analyze will also vary depending on different isotopes. So, for instance, potassium will turn to argon. So argon's over here. So argon's a noble gas. Okay. So the one thing is that potassium is obviously, well, what you need to do this analysis is a very potassium-rich mineral, don't you? Because you want potassium to be turning into argon. So you can't do it for something like let's say, a sodium plagioclase feldspar, because the amount of potassium in it is relatively low on the whole. Okay, so actually that was a terrible choice mineral. You can't do it for something like, let's say, an iron oxide mineral, because the amount of potassium in there is non-existent. So you can't use that dating technique on that particular mineral. Now, the gold standard for dating minerals, dating rocks, is normally uranium lead dating. That's the technique that most people will go to because it's, arguably, the most established and the most well understood. And, in the data that you collect is often pretty safe. So here are the half-lives for these different isotopes. So here we have uranium-238. The half-life is 4.5 billion years. So the uranium-238 that was present when the Earth first formed, we've just achieved the first half-life. Uranium-235 will go to lead-207. That takes 700 million years. Thorium to lead, thorium-232 to lead-208 takes 14 billion years. So, slightly older than the age of the universe at present. Potassium-argon dating takes 1.3 billion years. Rubidium-strontium, 47 billion years. And carbon-nitrogen, 5,730 years. So you'll see there's quite a big range in the half-lives. Okay, and here you can see certain minerals that we'll use to do this type of dating. So uranium lead dating, the mineral of choice is a mineral called zircon. Okay, now zircon's a great mineral for uranium lead dating. We'll discuss it more about it in just a second. For potassium argon dating, we'll use things like mica and feldspars because they tend to contain potassium in reasonably large quantities, and so we can obviously there'll obviously be quite a lot of radioactive potassium in them, and therefore we can use them for dating. Rubidium-strontium will typically use feldspars and micas and amphiboles. Rubidium-strontium is a bit more difficult to use as a technique. So, it requires a lot more skill and there's a lot more error in the data normally. So rubidium-strontium dating is kind of not used. It's mostly used in stuff that's very, very old. So rubidium-strontium dating was really used quite commonly for dating things like meteorites. And then we have carbon-nitrogen, so carbon-14 decay. And that's used for organic material. All right, and we'll be discussing that in a few slides' time as well. The other thing we need to remember is that some dating methods are more reliable than others, so the error will be smaller. So uranium lead dating using zircon is often considered to be the best dating technique out there by many people. It's considered, the data collected is very often considered to be quite good, and the error typically will be quite small. Okay, so what can we use isotopes for? The first thing that you're going to notice is that when we're talking about most isotopes, we are normally talking about igneous rocks or igneous processes. So for instance, one of the things that's easiest to date is something like a lava flow or a pyroclastic flow. Okay, so in this we're going to have things like mica minerals, which we can use potassium argon dating on, and we'll have zircons, which we can do uranium lead dating on. You know, if it's something organic like a piece of wood, we can of course date it using carbon-14. All right. If it's an intrusion like a granite, well, we can date that using zircons, so uranium lead dating again. We can also date contact metamorphism, because what we can do is we can date when the minerals in the contact metamorphic zone formed, because remember, they formed when the intrusion comes in. Okay, so we can date the minerals in the contact metamorphic zone to tell us when the intrusion actually made its way into that area. Because remember, when we date the granite, we're dating when the rock became solid, aren't we? Yes. So when the magma started forming zircon crystals. However, when we are dating the baked contact here, what we're actually dating is we're dating when the magma started heating up the rock. So those numbers are going to be slightly different, aren't they? Now, one of the things that we cannot date is we cannot date sedimentary rocks. Okay? The dating of sedimentary rocks is extremely difficult. Okay? For clastic rocks, you can't really do it very easily. You can do it for carbonates, but it's a very time-consuming, expensive technique, and the error on the data can be quite large. So you just have to bear that in mind. You can date carbonates, but very often it's not done unless there's no other possible avenue for dating. So sedimentary rocks cannot normally be dated. So note that excluding the carbon-14, the other processes are the result of igneous events. Okay, so what minerals are best suited for radiometric dating? Well, there's a few things we want. First of all, we want our mineral to be physically robust. We want it to be tough. We want it to be able to survive. Next, we also want our mineral to be chemically robust. So, let's say your mineral's in a rock that's 1 billion years old. Well, during that 1 billion years, your mineral isn't going to, just have sat there and had a nice, easy life. It's going to have been, it's going to have been exposed to hydrothermal fluids. Some of them may have been alkaline. Some of them may have been acid. And so you want your mineral to be able to stand up to those fluids and not alter. Because obviously if your mineral starts breaking down, well then it's completely useless, isn't it? You can't use it for dating. We want our mineral to be common. We want it to be everywhere. The more common, the better. We want our mineral to allow in the radioactive parent isotope, because we want as much of the parent isotope in the mineral as we can possibly get. But we want our mineral to not allow the daughter isotope. So let's go back to that uranium-235. We want our mineral to let in uranium-235, but not lead-207. So that means when we come along in 1 billion years' time and measure the mineral, any lead-207 we find in the mineral must have come from the uranium-235. And we also want our mineral to have what we call a high closure temperature. So the closure temperature is essentially the temperature above which your mineral can suffer leakage. So leakage is when you lose parent or daughter isotopes, essentially due to the mineral being heated up. So you want your closure temperature to be very, very high so that this isn't a problem. So just to go back to the closure temperature, here we go. So here's our example. So here's our crystal of, our unknown mineral. And as you can see, it contains these blue circles. That represents the parent isotope. Now, over time, the parent isotope is going to decay to the daughter isotope over here, which are these smaller blue circles. Okay. Now, what's going to happen is our mineral, so it started at 700 million years, it's now had 300 million years, so it's now essentially been around for 300 million years. And now what's going to happen is our mineral is going to be heated up above its closure temperature. And so what's going to happen is the daughter isotopes are going to be able to escape or leak out from the mineral. Now this means when we come along at the present day, well, we're going to get an incorrect date, aren't we? We're going to get essentially this date here, because at this point here, all the daughter isotopes were lost. And so all we had left were parent isotopes, and so we're going to assume this is when the mineral first formed. Note up here, all parent isotopes. So this is going to give us an incorrect date, so our date will be wrong. So this is why we want our mineral to have a high closure temperature, because we don't want this to happen. So here are some false color images of some zircons, and you can see that the chemical composition of the zircons is changing, but you can also see in this case, especially this one right here is a good example, how the margin has this lighter hue to it, and this could be the result of the crystal being heated up and some amount of leakage of the chemical components of the crystal taking place. So the chemical structure has altered slightly, the chemical composition has altered slightly, hence the different color. So the question is, well, why is zircon considered such a great mineral? Well, the first thing is zircon is very, very common. It will occur in igneous rocks, full stop, all of them. Okay, the amount will vary. Zircon's very common in felsic igneous rocks, pretty common in intermediate igneous rocks, less common in mafic rocks, and pretty uncommon in mafic igneous rocks, but it will be there in small amounts. Zircon is also very physically and chemically robust. It takes a lot to damage a crystal of zircon. Okay, so the chemical formula for zircon is zirconium silicon oxide. Now the nice thing is about zircon is it will allow the it'll allow the zirconium here to be replaced by uranium. So that means as the crystal grows, very, very small amounts of the zirconium in the crystal will be replaced by uranium. So as zircon crystals naturally have very small amounts of uranium in them. However, the crystal will not allow lead in. You cannot swap lead for zirconium. It just doesn't work. So that means as our zircon crystal grows, it's going to have small amounts of uranium in it, but no lead. And so this is the perfect situation, isn't it? Which is exactly what we want. The other thing about zircon, which is very, very helpful, is that the closure temperature is approximately 1000 degrees Celsius. So you've got to work pretty hard to make a zircon suffer leakage. So zircons are good for dating rocks which are typically older than 1 million years. If you date something that's younger than 1 million years, you are going to get erroneous data. So zircons have been used to date rocks. Essentially the oldest rocks and the oldest mineral on Earth have been dated using zircons. So there's another mineral called badleite, which has the chemical formula zirconium oxide, which can also be used for exactly the same reasons that we mention here. Okay? So this is why zircon is so good, because it lets in small amounts of uranium, no lead. It's common, it's physically and chemically robust, and it has a stupidly high closure temperature. It's pretty much the perfect mineral for radiometric dating. So just to let you see, so this is the Jack Hill zircon here. Now this is a false color image, by the way, so this didn't look like this, but this is the oldest mineral that's ever been found on Earth, and it was dated to 4.4 billion years. Okay, now we have a couple of pictures here. This is of pyroxene, and this is of the mineral biotite, and you can see that in this instance, notice how you have these brown circles surrounding these kind of colorless crystals right here, and right here. Well, these brown circles are caused by radioactive decay. So they're caused by the uranium decaying through alpha decay. If you remember, alpha decay kicks out a particle that consists of 2 protons and 2 neutrons. That's quite a big particle. So what's happening is as that uranium decays, that alpha particle is flying out from the zircon crystal, and it's slamming into the crystal lattice of the surrounding mineral. It's hitting it and breaking it and damaging it. And so what that results in are essentially these halos around the zircon crystal, which are the result of radiation damage. And they're called radiation halos. So in this case, you can see one in biotite, so the biotite's being damaged. In this case, the pyroxine's being damaged. So that's showing us that radioactive decay is actually happening. So we know there must be small amounts of a radioactive isotope in this mineral, and we know it's going to be uranium. So okay, so how do we use carbon-14 to actually date rocks? Well, no, sorry, rocks, that was a bad choice. Organic material. So, okay. So what we have is a case of cosmic rays coming from the sun that hit atoms in the atmosphere. So here we have our cosmic rays. It's going to hit an atom in the atmosphere, okay? And it's going to obliterate that atom. The atom is going to explode. It's going to send protons and neutrons flying everywhere. So if one of the neutrons hits a nitrogen-14 atom in the air, it is going to cause it to change to carbon-14. Okay, so let's run through that again. So if a neutron hits a nitrogen-14 atom, okay, it's going to cause that nitrogen-14 atom to throw away a proton to achieve balance. Okay, so one of these neutrons gets stuck onto a nitrogen-14 atom, and so in order to achieve balance, it has to throw away a proton, which it does. So if it throws away a proton, well, that means the proton number has decreased by 1. So obviously we have a new mineral now, don't we? Sorry, no, new element. I do apologize, not mineral, element. And so we go from nitrogen-14 to carbon-14. Okay, so once again, a nitrogen-14 atom, a neutron gets stuck onto it. Okay, in order to achieve balance, the nitrogen-14 atom has to kick out a proton. And this means, of course, because the proton number's changed, the element has changed. So it's now gone from nitrogen-14 to carbon-14. All right, that's relatively straightforward. Now this process happens at a fixed rate, which is really, really helpful. Now, what's going to happen to that carbon-14? Well, it's going to get absorbed into plants. Okay, remember, plants take in huge quantities of carbon dioxide, don't they? So it's going to absorb that carbon-14 into the plant through photosynthesis. Okay, so now we have our plants which contain carbon-14. Now remember, they're constantly replenishing their supply from the atmosphere, aren't they? Every day they're constantly taking carbon dioxide from the atmosphere and essentially using it to make organic material. So what's going to happen next? Well, we're going to have animals come along and they're going to graze on those plants, aren't they? And so the animals, the herbivores, are going to take the carbon-14 from the food they've just eaten, the grass, for instance, or the leaves on the tree. Okay, so then what's going to happen? Well, then what's going to happen is the predator's going to come along, the carnivore, and the carnivore is going to eat the herbivore. And so the carnivore is going to absorb the carbon-14 from the meat of the herbivore. So you can see we have this chain, don't we? And the carbon-14 is being passed all the way along it. And remember, the most important thing is this process is happening at a constant rate. Okay. So, well, why is this important? Well, the important thing is that eventually we die. So this means that we are no longer absorbing carbon-14, aren't we? Okay. Now, once an organic material dies, from be it a piece of wood all the way to a human being, okay, we're no longer taking in carbon-14. So what happens is the carbon-14 in our body slowly decays over time to nitrogen-14. Now the great thing is that because the amount of carbon-14 that was entering our body was pretty much constant, we already know how much carbon-14 there should be in our body. So all we have to do is measure the organic material and measure how much nitrogen-14 there is in it now. And from that we can work out how long it would take the carbon-14 that we had to change into the amount of nitrogen-14 that we can measure now. So it's a relatively straightforward process. The one limitation of carbon-nitrogen dating is that the half-life is very, very small. So if we're trying to date material, then the half-life is typically, I think it was said about 5,000 years. I'm actually going to go all the way back just to double check. Yeah, 5,730 years is the half-life. So that's a pretty small half-life. So that means the amount of carbon-14 in your piece of organic material will decay very, very quickly. So you need to essentially date younger material to get the highest amount of carbon-14 and nitrogen-14 possible. So obviously carbon-14 can be used to date anything, from organic material, wood, charcoal, leather, teeth, bones, etc. It can be also used to test very young, unaltered body fossils like mummified remains and frozen remains. Now the maximum possible date for dating something with carbon-14 dating is 50,000 years. And you can stretch it to 75,000 years if you use extremely special techniques. But to be clear, both of these processes require very, very large samples and very special processing techniques, so they're very expensive. Most material that we date using carbon-14 dating will typically be quite young, typically 10, 15,000 years. Okay. So all we need to know is how much nitrogen-14 there is in the sample, and then and because we know how much carbon-14 we started off with, and so it doesn't take that much time to calculate how much time it would take us to achieve the amount of nitrogen-14 we have, knowing how much carbon-14 we started with. So it's quite simple. Okay, so why are these numerical ages helpful? Well, okay, let's have a look at this particular diagram here. Well, here we have a granite which we've dated to 80 million years. Okay, well, what can this tell us? Well, instantly we know this grey rock here must therefore be older than 80 million years, mustn't it? So we know this, we know the granite must have intruded the grey rock, so the grey rock must have been there before the granite, so that grey rock must be older than 80 million years. We can also see, if we look right here, that the granite has been cut by this unconformity. Well, okay, we therefore know this unconformity must therefore be younger than 80 million years, mustn't it? Because it's cut a granite, that is 80 million years, so therefore this unconformity must have occurred later, so it must be younger than 80 million years. It also means that all of these beds of rock up here must also be younger than 80 million years. So, although granted the numbers we just applied to this diagram are very, very broad, you can get the idea, can't you? Okay, so here we have another diagram. Sorry, I'm just going to adjust. There we go. So, in this diagram we have 4 layers. No, actually just 3 layers. Normally do 4. Here's 3. A, B, and C. Okay, A layer, purple, B layer, green, C layer, blue. Now in this sequence we also have several layers that we can date. A lava flow to 18 million years, an intrusion to 12 million years, an ash flow to 8 million years, and a dike to 5 million years. So we can use these to help us date our layers of rock. Okay, so let's think about our layer A. Okay, well, superposition, it's got to be younger than the lava flow, hasn't it? Okay, so that means our lava flow here must be older than layer A. So layer A must be less than 18 million years old. We can also see that layer A is cut by the intrusion here. So principal of cross-cutting relationships. That means layer A and all these layers here which are cut by the intrusion must be older than the intrusion itself. So we know that layer A must be younger than 18 million years, but it must be older than 12 million years. Okay, hope that makes sense to everybody. Alright, so what about layer B? Well, layer B, as we can see, is definitely above layer A. So we know layer B must be older than 18 million years. We know that for certain. Now, the thing about layer B, as you can see, is not cross-cut by the granite. So we can't use that to date layer B. Okay? Because we don't know whether layer B was deposited, then the granite intruded, or we don't know whether the granite was intruded and then layer B was deposited, do we? We don't know which way around it goes. So the only other thing that we can use to date layer B is the ashfall layer up here. Remember, superposition. Layer B must be younger than the lava flow, but older than the ash flow. Yeah? Okay, so the lava flow, 18 million, so we know layer B is younger than the lava flow, but older than the ashfall. Okay, so now layer B is got to be older than 18 million years, but younger than 8 million years. And finally we have layer C. Well, layer C, once again, superposition says it has to be above the ashfall, so it must be younger than the ashfall layer, so therefore it must be younger than 8 million years. But as you can see, it's cross-cut by the dike here. Principle of superposition says therefore layer C must be older than the dike, so layer C must be younger than 8 million years, but older than 5 million years. Okay, and so this is how we're bracketing layers of rock. Now normally we can be much more accurate than this, but you know, this is, you know, just an example. Sorry, boring myself. Okay, so that's it, everyone. So please don't forget that the code word for the code word for this lecture is Lego. That's Lego as in the toy. All right, everyone. So take care, and well, keep an eye out for the next lecture video.